Namaste, welcome to the next video of Machine Learning Technique course. In this video, we'll implement model and inference components of linear regression model. We'll begin by importing necessary libraries for this task. You may recall that the training data for linear regression contains features and labels. The labels in case of linear regression are real numbers. And linear regression model uses linear combination of features to obtain the output labels. You know, in vectorized form, the label vector y can be obtained as a product of feature matrix and the weight vector w. Note that the model is parameterized by its weight vector and it is described by its mathematical form and weight vector. We will be implementing model inference in a vectorized form. And you are very well familiar with the vectorized form where we obtain the label vector y as a matrix product of the feature matrix and the weight vector w. Here n is the number of examples and m is the number of features. Y is a label vector, x is a feature matrix and w is the weight vector. The implementation is quite straightforward. We implement a function called predict that takes two arguments, x which is a feature matrix of shape n, m plus 1 and weight vector w with shape m plus 1, n. Note that there is one weight for every feature. That's why you can see that w has exactly m plus 1 weights and x has m plus 1 features for every example. And it returns the label vector of shape n, one label for one example. We first make sure that the feature matrix and weight vectors have compatible shapes. And once we assert that the shapes are indeed compatible, we go for the matrix vector multiplication. And we return the result of the matrix vector multiplication as the predicted label vector from this function. Now that we have written this function, it's a good idea to test it with some simple test case. Here we construct one such test case by hand. For testing the predict function, we have the following feature matrix x with shape 2, 4. Note that we have already added a dummy feature in this particular feature matrix. So the first row represents the features for the first example and the second row represents the feature for the second example. And we have weight vector w which has got 4 weights. Now we will multiply the features of the first example with the weight vector. So each feature gets multiplied with the corresponding weight and then we sum up the result of this multiplication across all the features. So in case of the first row, the product of the first row and the weight vector is as follows. So 1 gets multiplied by 1, 3 gets multiplied by 1, 2 gets multiplied by the third one and this 5 gets multiplied by this fourth one. And in the same way, we get the product of the second feature vector and the weight vector. So if we multiply them and add them up, we obtain the label or the output label of 11 for the first example and 21 for the second example. Now what we'll do is, with this particular test case that we verified by hand, we'll test the predict function. So there are roughly 3 phases in the test. First is the setup, second is where we do actual operation, and in the third phase we actually check the output that we obtain from the operation with the expected outputs. So here the training matrix is as we have used over here, you can see that it is a matrix of shape 2 comma 4. There are 4 features for every example, and there are 2 examples in this particular training matrix. Then there is a weight vector with a shape of 4. So that means there are 4 values of the weight vectors, 4 values of the weights in the weight vector. And then the expected label vector, we expect the output of 11 and 21 as the expected label vector, as we obtained in this particular calculation. Now we call the predict function with training matrix and weight vector as arguments, and we obtain the predicted label vector. We first check the shape of the predicted label vector and assert that it is indeed 2. And second, we check the content of the predicted label vector and check whether they match with the expected label vector. So we use this function called np.testing.assertArrayEqual, which tests whether 2 arrays have equal content. So we have expected label vector, which is 11 and 21, and we have predicted label vector. We make sure that both of them have exactly the same content. Let's run this particular test. You can see that the test succeeds. So that means we got the output from this particular function, which is exactly same as we expected. Now we demonstrate the model inference on the synthetic dataset. We generate dataset with number of samples equal to 100, number of features equal to 1, and with a data generation process whose parameters are 4 and 3. So Y, the output is obtained as a linear combination of the features, and we use a specific equation which is 4 plus 3x1 plus some random noise to obtain the output label Y. And the feature is sampled randomly from the random number generation. So let's generate the data set, and we add the dummy feature, and we perform train test split. Since we have not yet trained our model, we will use a random weight vector to get predictions from our model. So we obtain the random weight vector by calling np.random.rand with shape of 2, and we got a weight vector which has got the value of w0 to be 0.99 and value of w1 is 0.04. Now we obtain the prediction for the training set with this randomly chosen weight vector. The predictions will be stored in a variable y_hat. Let's compare the predicted values with the actual values. So first 10 predicted values are listed over here, and we'll compare them with the actual values which are listed over here. You can see that there is a vast difference between the predicted values and the actual values, and which is reasonable because we used a random weight vector w here, and we have not really trained our model with the optimal in order to obtain the optimal weight vector. And that's the reason why these predicted values and the actual values are far apart. The second important concept that we studied in our slides was the importance of the vectorized operations. So all of us are familiar with implementing machine learning algorithms or any other algorithms in a non-vectorized form, and we are all comfortable with it because that's how we have been implementing different programs. However, non-vectorized versions take longer time than the vectorized counterparts. We'll demonstrate this particular part with concrete data sets. So let's first implement a non-vectorized prediction function, and we implement a non-vectorized prediction function with 2 loops. The outer loop runs on the examples and the inner loop runs on the features, and in the inner loop we calculate or we perform the multiplication of the feature with the weight, corresponding weight, and we sum up the feature weight multiplication, and then we add that the resulting summation as the predicted label for ith example. Let us write a test for this function with exactly same setup as the vectorized implementation. So we use the same train and weight matrix, hence we have exactly the same expected label vector. We compare this expected label vector with the predicted label vector. So you can see that the test is passed. Now what we'll do is we'll compare the run times of vectorized and non-vectorized versions on dataset with 100 examples. So what we'll do is we will obtain the label vector for these 100 examples with vectorized implementation and non-vectorized implementation. And we'll record the time just before calling the function and after completing the function. And then we'll calculate the difference in the time to measure the amount of time that is spent to perform an operation. So here first we get the labels from the vectorized implementation and we calculate the time spent for the vectorized implementation. Second, we get the labels from the non-vectorized implementation, and finally we check whether both these label vectors are indeed the same. That's a sanity check. Now when we run this, we can see that the total time incurred in vectorized inference is order of magnitude lower than the non-vectorized implementation. And the content of both the vectors is the same. That's what we see from running this particular portion of the code. Since we did this experiment on a smaller data set, what we'll do is we will construct a larger data set with more examples and test the performance of vectorized and non-vectorized inference procedures. So next what we do is we generate a data set of 1 million examples or 1 million data points, and we perform the vectorized and non-vectorized inference procedure to obtain the labels for these 1 million examples. And you can see that the time it took for the vectorized implementation is far lesser than the time that non-vectorized inference took. So the difference is really of the order of magnitude. I hope this gives you a concrete demonstration of the utility of vectorized inference over the non-vectorized inference. And you can actually see this particular phenomenon across different components of the machine learning models. The vectorized inferences or the vectorized implementations are far superior in terms of performance than their non-vectorized counterparts. In the next video, we'll study the loss component of the linear regression model.